Okay, thank you for introduction. And first of all, I would like to thank the organizers for inviting me this interesting workshop. And I learned several new interesting things through this occasion. Okay, so I would like to talk about this time light cone gauge string field theory and propose the consistent light cone gauge superstring field theory. This is based on this paper in PTEP and with the collaboration with Ando-san, Fujii-san, and Totsuka-san. Okay, let me start some motivation as an introduction. As you know, there are two types of open super. Today, I concentrate on the open string theory. There are two types of string field theory. The one is that old-fashioned type, the light cone gauge string field theory. It is originated from the pioneering work by Kaku and Kikawa. This is the bosonic string case. That is consists only of the physical degrees of freedom, transverse oscillation mode of the string. It has light cone type interaction, joining splitting type interactions. And this action is local with time, with light cone time. And so canonical conjugation is possible. So from these reasons, the unitarity is manifest. On the other hand, another type of the string field theory is the gauge invariant string field theory that is originated from the Witten and our Kyoto group. The action is invariant under gauge transformation. That it has a so-called Witten type or symmetric interaction. So the question is that what is the relationship between the two formulations? Okay, that is these two has a quite different type of interaction. That one is the symmetric type, the one is the joining splitting type, light cone type interaction. So the relation is not so clear long time, but it becomes clear in the case. In the case of the bosonic string field theory by Ara and Matsunaga-san, they use the two key ideas. One is connecting the two types of interaction, different type of interactions through a field redefinition, and transform the gauge invariant theory with symmetric type interaction to the gauge invariant theory with light cone type interaction by field redefinition. And then eliminating the physical degree of freedom using the gauge invariant theory through the gauge fixing. So the question is, the question that can we extend this to the case of the superstring field theory? In the superstring theory, superstring case, there are two distinctive properties need to be considered. In the superstring case, that we need operator insertion is necessary for interaction. And then their collision causes divergence and leads to some difficulties. In the gauge, so the original Witten type superstring field theory has some difficulty. But in gauge invariant formulation, this difficulty can be circumvented by using homotopy algebra, A infinity algebra, that working given as by the Konopka and Ibo. So how can we resolve this issue in the light cone gauge theory? In the light cone gauge theory, there is also the similar type of difficulties I will explain later. In this talk, we construct a consistent light cone gauge theory by extending the Ara Matsunaga prescription, based on these two key ideas to superstring case. The first step is the field definition. By field redefinition, transform the Witten type gauge invariant theory to the light cone type gauge invariant theory, or based on the A infinity. This part is not related to our issue today, so I will skip this today. So second step, eliminating unphysical degrees of freedom. Okay, so we start from the Lightcon type gauge invariant superstring field theory based on the cyclic infinity algorithm. The action is given by this form. This form is appear several times in this workshop. This is invariant under this form of gauge transformation. Here, psi is a superstring field has two components, Nebuchadnezzar's component and Ramon component. And it is valued on the first quantized Hilbert space. But on this Ramon space, Ramon field, we further impose this constraint using the picture changing operator x and y. Xy is a projection. And omega, here this omega is a natural symplectic form on this restricted space, defined in terms of the symplectic form omega induced by BPZ inner product in the Hilbert space, inserting the inverse picture changing operator. なんか聞かなくなったよ。見なくなった。聞かなくなった。電池だの？はい。短くなり。Okay. And the string product M is a linear map from the n tensor product of the Hilbert space to the one Hilbert space, to n string to one string. Constructed based on this time the Lightcon type interaction and satisfied the following relation. The first is called the A infinity relations. Put M1 is set to be equal to BRS charge, and also the cyclicity condition with respect to this symplectic form omega. And before eliminating the physical degrees of freedom of gauge fixing, we first apply some similarity transformations on the system, given by this operator. S is exponential minus R, and R is given by this operator. And here, this X tilde is a non-zero mode of the longitudinal mode of string, this. And it twists this transformation twists the ghost system and superconformal current as follows. The BC ghost it has a dimension 2 and minus 1 to those with dimension 1 and 0. And beta gamma with dimension 3/2 and minus 1/2 to the 1/2, both have dimension 1/2. Then this superconformal current is originally vanishing central charge to the one with central charge 12. And also transform the BRS charge as it has this form QLC. One is the kinetic given makes a kinetic term, and the other is the genuine BRS charge, delta minus. Delta minus is given by this form, and this is just simple. This makes the transverse mode and the ghost mode just a simple curve. And we refer to this transformed object as those in the Lightcon frame. Okay, Lightcon frame, the mass operator of the longitudinal mode, Virasoro operator of the longitudinal mode, given this just those of the mode number counting operator. This is BRS exact by using this we call B0 parallel operator. So since this zero parallel is just a mode number, that is invertible on the subspace with zero non-zero part subspace. So if L0 is non-zero, the QLC cohomology is trivial in this subspace. The physical state in the N-Schwarz sector, those satisfying this L0 parallel is equal to zero, and given by this, or explicitly given by this transverse oscillator mode acting on the -1 XI -1 ground state. The physical state in the R sector is further restricted by this. In the Ramon sector, we have some zero mode of the oscillator, so we need some additional constraint for the physical state given by this type of oscillator. Here, the ground state is that the ground state of the covariance theory has that space-time spinner, 16 component SO19 spinner, and the right, if we add that this constraint, that reduced to the SO8 spinner, 8 component spinner. That is come from the BRS invariance of this light cone.
BRS closeness. That's condition that the state to be closed down.
Yeah, this delta minus has also the zero mode part.
Okay.
And closeness requires this additional cone.
Okay, thank you.
And so we can decompose the right cone Hilbert space to the transverse mode and parallel mode, longitudinal mode. And also the field also decomposed to part. By using projector, the projector of this subspace is, can be written as this form. We can explicitly write this form. And this transverse component contains physical degrees of freedom and will become the right cone gauge string field. But it still contains some physical degrees of freedom in its basis, Hilbert space, as we see later. Okay, in the right cone frame, the action is written as in this form by using that some such as similarity transformation. This is invariant under this transformation. Transverse part is gauge invariant. The longitudinal part is has gauge invariance. Here, the omega right cone is given by the similarity transformation by this relation. Here, AB is a right cone parallel component, perpendicular component. And string product is also transformed by similarity transformation. And so next we fix this longitudinal gauge imbalance on the longitudinal component. Here we fix this gauge imbalance by imposing this condition. It's analog of the Siegel gauge. So let the gauge fixed field longitudinal part satisfying this gauge condition using this gauge fixed field, the gauge invariant action is further written in this form. The bar string field has component, physical component and the gauge fixed longitudinal component. And here, the longitudinal kinetic term of the we can see from the this kinetic term of the longitudinal component. This is non-dynamical, and so integrating as follows. By introducing some so-called contracting homotopy operator in the language of the homotopy algebra, this is satisfying that this triviality inverse relation. Then some of equation motions of this longitudinal part of gauge fixed field of the longitudinal component can be written as this form. And the left-hand side is longitudinal path field. Then from this, we can solve this longitudinal component completely in terms of the physical field iteratively. So we can integrating out this longitudinal part. Then we have a right congruent superstring field theory. We can write the right congruent superstring field theory in this form. Here, the effective two product is just as similarity transformation and projecting to the physical perpendicular component. But the three-string product and higher has an original transformed product with and also that effective three-point product coming from the integration of the longitudinal part. And this, so we have infinite product of this form, but if it can be written in closed form using co-algebraic representation, as explained already some speaker in this workshop. The closed form is this form. And we expect that this is consistent right congruence theory, but it is still written using some physical degree of freedom as we see below. Okay, so what is the consistent right congruence theory we obtain? To see what action we obtain, consider the Nagoya-Ramon interaction term. We denote this form is written by this. With unlike this ABC is a string field, the A is a Nagoya field, but it still has some small number of physical degrees of freedom ghost and bosonite superconformal ghost. And this curly A has genuine physical oscillators. And B and C is a Ramon field, and it also has ghost, and also the longitudinal part of the psi zero. And to obtain the right congruent vertex, we evaluate correlation function of this physical part. In that case, we can replace that this similarity transformation only survive this fermionic part. Here we see that the bosonic part is not acting on this vertex. So the bosonic case that the vertex is invariant under this transformation, but the fermionic case that we need some additional transformation is remaining. And so we evaluated, but from some H0 charge conservation, only the linear term of this R can survive. And we have we can rewrite this is to the picking up only the linear term and evaluate it as a correlation function of the upper half plane. Here, the transformation contour of the transformation is originally just around each vertex operators, but we can deform this integration contours around each vertex point to that around the interaction point we call the zero. And interaction point is given by this zeros of this d rho dz. So d rho this factor d rho dz inverse gives a pole at the interaction point, and we pick the integration picks up the interaction point operator. Then the three-string interaction has this form. This is just a genuine transverse field with that supercurrent insertion at the interaction point. And we can similarly evaluate the Nagoya three-point interaction term using the similar method. in this time that we need some one picture changing operator, so the calculation is a little complicated, but little calculation we find that the similar, we obtain a similar type of interaction, genuine 3-point interaction with supercurrent insertion at the interaction point. Although these results are consistent with what is already known, but they give rise to difficulties arising from the collision of this supercurrent at the interaction point. Here, I must note that the interaction point always collides in the TU channel's post-ring scattering. In the S channel or ST channel diagram, the interaction does not collide, only collide with a special case. But in the TU channel scattering, this form, first string 2 split 2, 3, and an intermediate state, and string intermediate state join the string 1, and then makes a 4. And then this interaction point here and here, so if the propagator shrinks, the interaction point always collide. And this is the interaction point goes down. This represents that the genuine force-ring interaction, and then comes up another propagator region. There is no divergence in the. However, since there is no divergence in gauge invariance theory, this divergence must be cancelled by some other contribution. In any case, some regularization is needed because of this divergence. So we consider theory with stubs. Due to the stubs, interaction points do not collide in the propagator graphs, propagator region, in the stubs theory. This shaded region, gray region, is that non-local interaction with stubs. Then that when this propagator shrinks, the two interaction points does not collide. Instead, the moduli region where the interaction points collide are included in the genuine force-ring interaction. Genuine in quote. The genuine force-ring vertex with stubs include this original force-ring interaction with that remaining region of the Feynman graph region. This stage.
The very last stage. So you started from the gauge
from the first gauge invariance theory, yes.
So you started with the gauge invariance with inside interaction.
Yes.
So you introduced the stubs in that theory, or which in the very last stage?
First stage.
That seems to be changing the theory.
Yes, yes.
You're changing the theory.
Yes.
Is this okay?
Yeah.
Are you sure?
Yeah.
Okay.
But of course, we can take a limit to the established limit and consider the stub length is some regularization. So the force-ring. So the question is that this force-ring interaction, the stub theory has whether the divergence appear or not. So before the detailed calculation, first let us consider the massless four-Raman interaction vertex using this Mandelstam mapping describing the TU channel scattering. The alpha 1 and alpha 2 is positive, alpha 3 and alpha 4 negative, and the vertex point is ordered this order. This order represents the TU channel. And considering that Z1, Z2, Z4 are fixed using SL2 invariance, we choose the D3 as a model. The interaction point d plus minus are determined by this equation as a function of x, using this implicitly determine this relation. The right gauge massless for interaction is given by this form. We here transformation explicitly act on the vertex, then obtain this types of transformed vertex. And so genuine four-Raman interaction vertex is evaluated by this correlation function for transformed vertex operators with that. And the four-string interaction has one moduli, so we need B ghost insertion. And the ghost sorry?
The genuine four-Raman interaction vertex. Did you add by hand?
No. This is originally.
Was it originally there?
Yeah. In the light gauge field theory, the original there is four-string interaction from the first.
Okay. So, but is that vertex originally from with the stubs, or did you?
Originally, no, without stubs.
Without stubs.
Yeah, but we add the stubs by considering the decomposition of the force scattering amplitude.
Okay, so I see.
Yeah.
You introduce stubs to
this.
Moduli is covered.
Okay. Originally, moduli region is this region, but at the additional region does not come from the stub.
Okay.
Diagram.
Okay.
Yeah, this B ghost contour of this B ghost insertion is this around the D2, D3, and one of the interaction points. The moduli X is related to the right time by this relation, and right time and the relation of the right time and moduli X is determined by this equation. So now we can evaluate the correlation function except for the spin operators. This, of course, can also be evaluated by in principle, but we remain that and also calculate other parts. And we eventually obtain this form, and this reproduces a part of the TU channel amplitude, superstring amplitude, and there is no divergence at moduli points at which that the interaction point coincide. So at least in the massless four-string vertex, there are no divergence. So how does divergence that existed in the starpless theory vanish? An alternative calculation can reveal what happens. So remember that how we evaluate the three-string interaction, the transformation remain does not acting on the vertex and remain this form. And without applying B, we evaluate it as in the correlation function. This time, the H0 charge conservation gives that two insertions of this RF is only these two RF insertion remain survive and can evaluate this form. And this contour of this transformation is originally, of course, at each point twice, but we deformed it to this form, both interaction points twice. And this contour can also deform three types of some of the three types of contour. One is that the interaction one of the interaction points z minus twice, and d minus and d plus once, and d plus twice. This second contour generates the supercurrent insertion at each interaction point, and it reproduces the calculation, including the divergence performed using three-string interaction in the statless cell. However, there are also contributions from this first and third contours that is evaluated in this form. So by adding all the three contributions together, we have this kind of amplitude, this forcing interaction, where we don't explicitly write the function a and bij. This is a function of the x and zi that is finite at x equal to x plus minus. So our claim is that this stub theory gives a consistent right congruent superstring field theory. So, a conclusion to discuss. We studied that a consistent right congruent superstring field theory has been obtained by eliminating unphysical degrees of freedom from the gauge invariant theory with right cone type interaction with stubs. And the remaining problem is that even at the such stubless limit, the divergence does not appear in the four-string interaction. Yeah, this calculation does not depend on the length of the stubs. That only appear in the region of the moduli, integration of the moduli. So the divergence in the propagator graphs caused by the collision of three-string interaction points should be cancelled by contribution of the remaining part of the effective four-string interaction, the part obtained by integrating out the longitudinal degrees of freedom. But we cannot yet show it explicitly. The problem is, how can we show it explicitly? And also, for quantum consistency, the right congruent superstring field theory, or in general, right congruent string field theory must also incorporate closed string field explicitly. So the question is that can this fact can be derived from some requirement of the quantum infinity algebra, quantum consistency of the gauge invariant theory. And also, what extent can we extend this result to closed superstring field theories? Okay, that's all.